Cool. Hi. So I want to talk to you a little bit about how the GC is actually set up, and then we already kind of went through how to inject a sample, how the peak simple works, but I want to talk about, before you even start all that, how to set things up and why you'd want to set it up that way. So the first thing is in your carrier gas selection. So for my particular instance, so for the how to use this GC Sarah Jean's way, I'm looking for carbon dioxide, I'm looking for oxygen, and I'm looking for nitrogen. And so that means that helium is an optimal carrier gas. And so helium is going to be able to show, it doesn't have the same thermal conductivities, is that right? Well, whatever, as oxygen and nitrogen do. If I had like a nitrogen carrier gas, you would never see nitrogen show up because it would blend in with the carrier gas. And I want to focus your attention on the pressure of the carrier gas and the pressure inside of the GC. So the pressure right now is set to about 40 psi. Your pressure should always be about 15 psi higher than what you have the GC set to. And the pressure in the GC is set with a little screwdriver, and if you look at the side of the tank, side of this, it's going to tell you what flow rate your pressures are going to give you, and then the flow rate and the pressure. So the pressure, which regulates the flow rate, is going to determine at what time your peaks show up. So what time your nitrogen, oxygen, and carbon dioxide show up. And so what you do is to look at so the local and total set points are basically the same thing, but you're going to want to go to this switch. And and right now it's facing down, so it's only going to show you the temperature in column 1. I want to see all of the buttons, and so I switch it up, and then I press this button, and then when I press this button, it's telling me that I'm at 16 psi. And so that's going to be a slightly slower flow rate than the 27 they recommend, but it's what works for me. And so the local, like I said, when you change the local, so if I were to take this screwdriver and put it in here and turn it right, it would increase in the pressure. If I can reach it. And so you can watch it go up in pressure. So right, so you see how it's 18, 19. So I'm gonna put it back to 16 because that's what we want it at. And I don't wanna mess it up. But then you're gonna go into the actual, and that'll adjust accordingly. If you have any problems with your peak showing up, or if you notice something doesn't look right, one of the first things you should troubleshoot is if there's a leak. And to do that, you're going to be using this area. You're going to be looking at the pressure here. And so what you would do is, this is where the carrier gas is ultimately leaving. This is the only place it should be leaving. And so if you put in a compression fitting, or even if you just attach a tubing and you clamp it shut so that there's no air bubbling out of it, then you should be able to turn off the instrument or turn off the pressure, and the actual pressure will not decrease. If you see a decrease in pressure when it's supposed to be holding the pressure, that means there's a leak in your system. And so then you have to backtrack, starting from here and working your way backwards to see where the leak is. And that is described in detail on the SRI website and also linked within the SOP. And first of all, when you're running the carrier gas, you have it at a certain pressure. You can visually see how different the bubbles coming out of it, so the carrier gas coming out, they'll be much quicker for a higher flow rate and much slower for a lower flow rate. So you can tell there's a plug in the system, right? So the opposite of a leak, if this is coming out at a much slower rate for the same pressure. So if this was coming out, only half the amount of bubbles, I would know there's something clogging it. So something's either there's a piece of silicone or Teflon tape inside of here, and gas is not able to get through. There's a lot of moisture inside of the columns, what have you. Okay, so we talked about the carrier gas, we talked about how to see the flow in the carrier gas, we talked about troubleshooting a couple things, which is in further detail on the internet and on the drive. I want to show you guys what the inside actually looks like. Starting with the injection valve. So we mentioned that the injection valve is only 1 milliliter in size, and so you cannot control the size of your sample. So it's a little bit tricky. So we have the actual 10 mils, and then we have this kind of dead space here, right? So every time you inject it, you want to flush out that dead space, but ultimately you see that tag right there tells you that it's a 1 milliliter sample loop, and so only 1 mil is going to be allowed to actually reside in here, and then all these different things are going to decide what it's opening and closing to allow your sample to start. So when you press that start button, that's when it's going to open the valve and it's going to analyze that 1 mil. And so that's why it's crucial that you flush it and then start it in the middle of your second flush. And that's why we found that that works best. And then, okay, before I show you the gel and the molecular sieve, I'm going to draw your attention to this event table. And so in reality, it's a little bit more intimidating and complicated to look at this and try to figure this out than it would be just to know how to use this instrument. But all it's really trying to tell you is where the carrier gas is going to be heading through when it goes between the silica gel column and the molecular sieve. The molecular sieve's job is to separate out the components, and the one very big issue with this is that if you have too much carbon dioxide going through the molecular sieve, over time the carbon dioxide will clog it up and you won't see a very good peak. It's the same thing with moisture, is if you're constantly injecting things that have a high moisture content and you don't have a filter to try to negate that a little bit, then you're going to just slowly accumulate moisture until your peaks look like crap. And so to avoid that, in your event table, you need to find at what point your carbon dioxide peak is going to be, and so it takes a bit of experimentation. So what I did was, since I'm only looking for carbon dioxide, oxygen, and nitrogen, I would take air, I would have this filter, and then I would inject it at a certain pressure, and I would figure out how long it took for me to get an oxygen peak, and I would set the valve to change right after that, so I knew that I was only allowing oxygen through. And then I did that, I would increase the time period a little bit for nitrogen, and then I would increase it little by little until I had all of the oxygen and all of the nitrogen peak, and then I would switch the column immediately after that so that I knew that I was safe. As it turns out, the peak between oxygen, nitrogen, and carbon dioxide is pretty significant, and so if it takes about 2.7 minutes to get to the oxygen peak, and it takes about 3.5 minutes to get the nitrogen peak, it's going to take about 11 minutes, or I guess about 9-ish minutes to get to the CO2 peak. And so we have it switching at 5 minutes. If we increased the pressure, everything would be sooner, and so we'd have to increase this sooner. Contrastingly, if we decrease the pressure. So that should make sense. That's not explicitly stated anywhere, or it wasn't before this, and so it's important you understand that. So now we can actually take a look inside of this and what this is. So these are a little bit overlapping because we had to replace the sieve because it was not separating. But what you're looking at here is this is the sieve. This is the molecular sieve. So this is what's doing the separating of the oxygen and nitrogen. This is what you don't want to get oxygen in. And over here is the gel column. And so, as I mentioned earlier, if you're looking for leaks or anything like that, you would start over here where the carrier gas comes out, and you would start working your way backwards and say, okay, is there a leak here? Is there a leak here? Is there a leak here? And as it turns out, there was actually also a leak. One of the connections connecting the silica gel and the column were not tight enough, and so we had to tighten those.
For the sieve, just real quick, you said you don't want oxygen in the sieve. Is it CO2?
Oh, I meant CO2.
CO2,
yeah.
gotcha.
So, oxygen goes in the sieve. That's
okay.
Fine. My bad. CO2 is not allowed in the sieve. If you're going to replace the columns, which you really should never have to unless they're being abused, for some reason our lab has gone through 2 of them in like 3 years, and I don't understand why, because they should last you forever. But if you do need to, be very cautious, because if you get anything, any dust particle or anything inside of these columns, they're shot. So if you're going to replace a column, but then there's Teflon tape for some reason in a compression fitting, or something weird is in here, or you just don't care, it's going to just be clogged up and broken, and you cannot bake it out. Which baking is another important thing. If you're getting bad peaks, or if it hasn't been used in several years, their chances are is that your columns are full of moisture and crappy. And so you want to bake it, which is explicitly stated how to do so. It's very easy. And I'm just going to direct your attention to where the buttons are that are mentioned in the SOP. I won't go into all the details of it. I just want to show you where the switch is for the 5-minute bake. So when you start a bake, when you first start it and everything's ready to go, you have flow with your carrier gas and you have the temperature, this is what you will switch on before you leave it for 20 hours or however long you choose to bake it for. This goes on first. Over here, the cell and the column oven and the column oven max, you're going to adjust this the same way we adjusted the flow. You're going to take your screwdriver on top, and then you're going to have this on display all, and you're going to take a look at what these are set for, and you're going to make sure they're set back to what they are. Notice that this should not exceed 220. You should be able to adjust that somewhere, and it should say that somewhere, and I cannot see where. And then this should be set back to 0 when you're done. Oh, probably the most important thing that I haven't even mentioned yet. Okay, we talked about this, we talked about the insides of this, we don't want to get CO2 or any kind of crap in this. Really, 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 really important that NIML has stressed, and I have stressed, maybe not as much as NIML, but that you need to wait until there's carrier gas flowing before you turn on your TCD. And so you will just take your water, you will just put it in here. If there is flow and it looks correct to you based off of your experimental past and what you know to be true, so I know that that looks correct to me, that is when and only when you can turn this on. I suggest that when this is in the off position and you are first running a sample, that you put it on low just to make sure that your samples look correct. When you are ready for your real results, I have found that it is easier to find a peak at high. And so I have done all my calibrations in the high position. So when you're ready to shut down the GC, this is the first thing to turn off before you touch anything else. That should just about cover everything with the GC. Do you have any more questions, Noah, that I should cover? Okay, cool. Thanks.